How are Transmon Qubits engineered? Imagine building a tiny, super-sensitive electronic circuit that can hold quantum information. That's what engineers do when they create Transmon qubits. These are special superconducting circuits designed to work as quantum bits or qubits. They are built to last longer and resist noise better than older designs. The main part of a transmon is a small superconducting island or loop. This island is connected to the rest of the circuit through one or two Josephson junctions. These junctions are super-thin insulating barriers sandwiched between superconductors. They allow pairs of electrons called Cooper pairs to tunnel through, which creates a nonlinear inductance. This nonlinearity is what makes the transmon useful for quantum computing. To make the qubit more stable, engineers add a large capacitor in parallel with the Josephson junctions. This capacitor spreads out the electric charge, making the qubit less sensitive to charge noise. It also lowers the energy needed to add charge to the circuit, which helps it maintain coherence longer. The process starts with choosing a good substrate, usually sapphire, because it insulates well and works nicely with superconducting films. Then, a thin film of superconducting material like tantalum, niobium, or aluminum is deposited onto the substrate. Tantalum is popular because it can produce qubits with longer coherence times. Next, the circuit pattern is created using photolithography or electron beam lithography. These techniques allow precise shaping of the capacitor pads and resonators. The Josephson junctions are made by overlapping aluminum layers separated by a tiny aluminum oxide barrier. This is done with a special double-angle evaporation process called the Dolan bridge method. Sometimes, the design includes a SQUID or superconducting quantum interference device loop made of two Josephson junctions. This setup allows engineers to tune the qubit's frequency by applying a magnetic flux. The large shunting capacitor is often shaped like a cross or an X to improve connectivity and reduce electric field concentration. This helps lower surface losses and improve performance. The transmon is then connected capacitively to a readout resonator. This resonator helps measure the qubit's state by detecting tiny shifts in its frequency. These shifts depend on whether the qubit is in a 0 or 1 state. The entire fabrication process involves cleaning and preparing the substrate, depositing superconducting films, patterning the circuits, etching unwanted material, and forming the Josephson junctions. Between each step, cleaning is essential to keep the device free from contamination. Once finished, the device is cooled down to very low temperatures, around millikelvin, in dilution refrigerators. This keeps the superconductors working and minimizes thermal noise. Thanks to this careful engineering, transmon qubits can last hundreds of microseconds to milliseconds, making high-fidelity quantum operations possible. Their planar design also allows for integrating many qubits on a single chip, which is key for scaling up quantum computers. To sum it up, transmon qubits are built by combining superconducting materials, tiny Josephson junctions, and large capacitors, all designed to work together smoothly. This engineering approach is at the heart of many modern quantum computers, helping us move closer to practical quantum technology.